Hello grade 11 students. Today I am going to discuss with you all the third lesson of your grade 11 science textbook, that is mixtures. So when you hear that word, you know this is things mixed together, or there are more than one substances present together as one. That is where we talk about mixtures. In our day-to-day life, we use many things and we come across many things that are mixtures. For example, from the morning you use so many things. You eat and drink so many things which are made up of mixtures. The tea you drink or the coffee you drink, a fruit juice, substances that you eat, and most of the things that you do in school involves lot of mixtures. For example, when you draw, if you are in an art class, you use paint, you mix colors. So in many instances, we use mixtures. The same way, if we look at our environment, that has lot of mixtures. Around us is the atmosphere. The atmosphere is made up of many gases that you already know. Nitrogen is there in about 78%, oxygen 20%, and carbon dioxide, water vapor, noble gases, like that there are many gases mixed together and they form the air of the atmosphere. So that means mixtures are very, very important to us in many different ways. That is the reason why we need to learn about mixtures. So first we look at the contents of this lesson. Type of mixtures, composition of mixtures, and separation of compounds in mixtures. So although I said there are many types of mixtures, they belong to different types. That is the type of mixtures. And in each type, the components are mixed in different quantities. That is why we need to learn the composition of mixtures. And when you have a mixture, if you are unable to separate out anything, then sometimes the mixture is not useful to us. So that is why we need to know separation of compounds in mixtures. So to start off the lesson, I will revise something that you learned in grade 10. Matter. You know what matter is? Anything that occupies space and has a mass. And matter is divided into two types. What are they? Pure substances and non-pure substances. How do we differentiate them? Pure substances contain only one type of matter. And because of that, there are two main types of pure substances. What are they? The elements Elements, as you know, are made up of only one type of atoms. You know many examples: carbon, sodium, argon. These are all elements. I have used the symbols. You are very familiar with them now. Then we have the compounds. Compounds are also pure substances. They are made up of one type of molecules. For example, water is made up of water molecules. And water molecule is formed by the chemical combination of oxygen with two hydrogens. So you know compounds: H2O, water, Then we have NH3, ammonia. We can even have copper sulfate, CuSO4. So all these are compounds. You all are very familiar with elements and compounds. Then you know what non-pure substances are. There are more than one pure substances mixed together. Therefore, we call them as non-pure substances, or now we give the name mixtures. So, I will rewrite the name here as mixtures. That is our lesson today. And you know already how to classify mixtures. There are two types of mixtures, the homogeneous mixture and the heterogeneous mixture. Homogeneous mixture and heterogeneous mixture. Very common mixtures. The salt solution that we use at home is a homogeneous mixture. So, salt solution. Or if you take the lab, a hydrochloric acid solution, that is a homogeneous mixture. So, I'll just say acid solutions. Similarly, you know examples for heterogeneous mixtures. Rice and sand mixed together, or ice cream are examples of heterogeneous mixtures. Rice and sand, or we can say ice cream. These are all different types of mixtures. So, already you know what mixtures are and how they can be classified into two groups, homogeneous and heterogeneous mixtures. But in this lesson, we will see how scientists have identified mixtures and how you could identify a mixture and how you could use it for your requirement, as well as more information about their properties and also the two different types of mixtures. So, with that introduction, I will move on to the lesson. Types of mixtures. Matter that contains two or more substances is referred to as a mixture. This is something that you already know, we discuss now as well. Two or more substances. Mixtures are not pure substances. That also we have discussed before. Why? If we take the atmospheric air, although we refer to it as air, it contains many gases. We have discussed it now. Nitrogen, oxygen, carbon dioxide, water vapor, and many other gases. You take the soil. Soil has many minerals in it. It has sand, it has clay, it has soil water, soil air. So, that contains more than one substances. Therefore, it is not a pure substance. And natural environment mostly contains mixtures. So, the two examples that we discussed. Air. Air contains nitrogen gas, oxygen gas, carbon dioxide, water vapor, etc. It can also have dust particles in it. There can be impurities. Another example. the soil. It contains sand, clay, it can have stones. Then there can be organic matter. In addition to that, the soil can have air, or it actually has air and water. So as you can see, the two main components around us, the natural components, both air and soil, are mixtures. They are not pure substances and they contain more than two components, two or more components. Like this, you can think about many other examples. If we take the sea water, we see it as water. But if you taste it, I am sure which you would have done it before, you know it is very, very salty. The reason is, in addition to water, there are many salts dissolved in it. We have discussed this in your previous grade as well. There is sodium chloride, magnesium chloride and many other salts present. So, sea water has water as the main component. In addition to that, there are salts like sodium chloride and magnesium chloride. So, these are examples from the environment. I told you all the cup of tea that we drink has many components. You need to have tea, you need to have milk, then sugar and water. So, there are 4 main components present in the cup of tea that you drink. So, mixtures are a very important component of our life. We will try to understand the properties of mixtures by doing an activity. Activity: study more about the components of a mixture. To do this activity, we need these materials. The first one here is copper sulfate. As you can see, here we have the hydrated copper sulfate, that is why it is blue in color. And the anhydrous copper sulfate, you can use that as well, is white in color. Then we have the naphthalene balls. Naphthalene balls. Naphthalene balls are available in the household as well. You would have seen them, the naphthalene balls. Then we need the mortar and the pestle. We need a glass funnel. A glass funnel and a glass rod. And these are filter papers. We use a funnel having a filter paper to filter substances from a solution. So, here we need filter paper. And also we need a beaker and we need water. So, this is a very simple activity. There are 2 parts to this activity. In the first part, what we do is we take the copper sulfate and naphthalene. You powder the naphthalene and you can observe the 2 substances closely. You can see there is a difference in the color as well as the difference in the crystalline nature. And then we mix the 2 substances. copper sulfate and naphthalene are mixed together by transferring them into the mortar and by grinding it using the pestle. Or in another way, we can first take the copper sulfate, into that we can put a few naphthalene balls and grind it so that they mix together. Or else you can take the two powders and you can mix them together separately. Either way, we need to get a mixture of naphthalene and copper sulfate. And then you have to observe and see whether you could differentiate the particles present in that mixture. That is the first part of the activity. In the second part of the activity, we dissolve that mixture. The copper sulfate naphthalene mixture is transferred into a beaker and we add some water to it and dissolve it well using a glass rod. When dissolving, again you have to observe how the two substances dissolve, whether they dissolve or not. And then the resulting solution or the mixture is filtered using the glass funnel and filter paper. We have to fold the filter paper, place it inside the glass funnel, and we will need a conical flask or we will need more beakers, and into that we can filter the solution. I will go through the method again and then we will do the activity. The method: take some copper sulfate and naphthalene, that is mothballs, into a mortar. Grind them together with the pestle into a powder and mix well. So here our main purpose is to mix the two substances. Transfer the powder onto a piece of paper and observe. So we will observe how the two substances will look like in the mixture. Whether you can differentiate and identify them separately or whether you cannot differentiate them and identify them individually. Transfer the mixture into a small 100 milliliter beaker. This is the second part of the activity. Add about 50 milliliters of water to it and stir well. Place a filter paper in a funnel and filter this solution into another beaker. So we are filtering and trying to separate the two components of the mixture. Allow the residues on the filter paper to dry and observe with a hand lens. So the word residue. Observe the filtrate as well. So here when you filter into a beaker using a funnel, the solution that you get here is known as the filtrate, and the substance that remains in the funnel is known as the residue. So substance that does not get filtered into the solution and which remains in the filter paper is the residue. So since the residue will have some water in it, it will be wet, we have to allow it to dry and then observe. And the filtrate also has to be observed clearly. So this is a simple activity. Now let us do this activity in the lab. Okay students, so we are going to do the activity to show that pure substances can mix and form mixtures. For that we need these materials. I have hydrated copper sulfate here. You can see the crystalline shape and the blue color nature of the hydrated copper sulfate. Then we have the naphthalene balls here and the mortar and pestle to grind the naphthalene into powder. Then again, since I am going to do both activities together, the first and the second activities, I have a beaker to which I'll be transferring the substance, and I have water to dissolve the mixture, and later to filter the mixture to separate the components, or to observe whether we can separate the components. So first I will have to transfer the naphthalene balls into a mortar and pestle, and then I can grind it together. Grind it, or if I just press it itself, I can get the powder because it is a soft ball. We can easily powder it without any problem. Now students, you can observe these are two substances. One is the blue color crystalline powder and the other one is the white color crystalline powder. Now we have to mix the two powders. I will transfer it. Okay, to this I will add copper sulfate. Now I'll mix them both together. Now the two substances are mixed together completely. So here we have a mixture, but you can't really pick out the two substances. The naphthalene and the hydrated copper sulfate is visible to you. If it's not clearly visible, you can even use a hand lens and observe it more closely. Here again, you can see both the colors, but you can't really differentiate and separate them out. So this is a mixture. Mixture is a substance where more than one pure substances are mixed together and they exist together as one. So this is where you understand what mixture is. Then I will move on to the second part of the activity, or the second activity in your textbook, where I will dissolve this substance. I will transfer it into a beaker. Transfer the mixture into a beaker. Now that I have transferred all the solid into the beaker, I will add about 50 milliliters of water. As you can see, this is a 100 centimeter cube beaker, a small beaker. To that, I will add about 50 milliliters of water. This is not a quantitative activity, so we don't have to measure the volume exactly. When I mix the components, you can see the solution becoming blue in color. And also at the sides, you can see a white color solid remaining. Even in this, you can see that there is white color substance that has not dissolved in water. So here students, you can observe that all the three components, water, copper sulfate and naphthalene, are mixed together. So we have a liquid mixture. In that you can see the white color solid particles on top. Now what I will do is, this is a filter paper. I'm going to fold the filter paper. I have folded the filter paper. I open it up and place it inside the funnel, and I will set a beaker under the funnel. Then if we put a few drops of water, the filter paper will stick to the funnel. To make sure that it sticks to the funnel properly. Okay. Now I can transfer the solution into this. So here I will filter this solution. You can see, students, this is how we set up to filter substances. A beaker is kept, a funnel is fixed to a stand so that you don't have to hold it and there is enough space so the solution can flow down. Filter paper is there, that is the full funnel, and we have to make sure that the solution does not go out of the filter paper. It has to be within the filter paper. Here you can see the clear solution flowing down through the funnel and is getting collected in the other beaker. I will transfer. If I touch it to the wall, then it will flow faster. You have to make sure that you transfer all the components. Still the mixture is getting filtered. So you can see now all the solution has filtered. Here you can see the clear solution. It's a blue color solution. And inside the funnel, I have solid substances left. So this is something that you can observe here. And this process where we filter this, it's known as the filtration process, and you all know it's a physical separation method. So if I transfer the solid substance that is there inside the filter paper onto this colored cardboard, we will have to really dry it and observe. For now, I will show you all that this is a white color solid substance. Remember, students, this is only for observation. We are not going to weigh the amount of substance. Otherwise, we will have to dry it completely and get all the solid here. Now, here you can see this is only the white color solid. That means this is only naphthalene. And here, as you can see, copper sulfate is blue color, and we have got the full copper sulfate into this beaker. First, we had the two substances individually, copper sulfate and naphthalene. We mixed them together, got the mixture, couldn't identify the components separately. Then we dissolved it and filtered it, and by doing this physical separation, now we have the two components separately, naphthalene and copper sulfate. Even this copper sulfate can be poured into a large container, one that is flat but has a larger area. You can pour it into that, and if you allow the water to vaporize, then you can get the copper sulfate crystals back. So these are all physical methods of separation. From this activity, you all can understand, students, mixtures are made up of more than one pure components, and it is mixed together, but when it gets mixed, the chemical properties, you can see the chemical property of naphthalene hasn't changed, chemical property of copper sulfate has not changed. So chemical properties doesn't change, and also the components of a mixture can be separated by physical methods. Okay, students. Now you saw the observations of the two activities we just did. Initially, you were able to see the blue colored copper sulfate and the white colored naphthalene. Both were solids. And when they were mixed together, you saw that as one solid powder. You are not able to exactly differentiate the copper sulfate particles from the naphthalene particles. Although you see the blue and white color mixed together, you cannot directly differentiate and identify the particles separately. So that is a property of mixture. One, the mixture is made up of two components, naphthalene and copper sulfate. Then you saw that we could not differentiate the particles easily. But during the second part of the activity, when we dissolve it in water, you saw clearly a blue color solution was formed, or it dissolved and the solution became blue in color. But in that blue color solution, you saw white color residue, component that did not dissolve in water. And then we filtered the solution. There, the filtrate, what you collect in the second beaker, was a clear blue color solution. And what we get in the filter paper, that is the residue, was a white color substance. And once we dry the white color substance and observe it clearly, you will see they are naphthalene particles. The dry solid naphthalene. You can identify it easily. And because the filtrate, the solution that remains in the beaker, is blue in color, you know that is copper sulfate solution. So those are the observations of the activity. First, we will write down the observations. Naphthalene and copper sulfate cannot be differentiated clearly in the mixture. After dissolving and filtering, clear blue color solution and white color residue are obtained. So from these two, what can you conclude? We can conclude that mixture is made up of two or more components. And dissolving and filtering are physical methods of separation. So from that, by doing a physical separation, we were able to separate the two components. That is the naphthalene and copper sulfate. And you all know the solution is copper sulfate. If we want, we can pour it into a large container, and if we allow the water to evaporate, we will get the copper sulfate crystals back. So there we can get the two components back by physical separation method. So that is another property of mixtures. And also, initially you saw that naphthalene was white color crystalline powder and copper sulfate is blue color crystalline powder. After mixing and separating, again you get the white color crystalline naphthalene substance. So that means when substances mix together and form a mixture, their chemical properties does not change. They remain the same component. So those are the conclusions that we can get from these activities. So the first one, mixture contains two or more substances. In this example, two substances, and we can components of a mixture can be separated by physical methods. And the third one, the chemical properties or properties of the components remain the same. So those are the conclusions. Based on this, we can define mixtures. Mixtures are matter consisting of two or more components which are not chemically combined and can be separated by physical methods. So here you can see consisting of two or more components and they are not chemically combined and can be separated by physical methods. So we were able to observe all these three properties of mixture. So we will look at some examples. You can see here in this table some mixtures are given and the components present in those mixtures are given to you. The first one, cement mortar. This is a mixture that is used to make buildings. The walls and the structure of a building is mainly made with cement. So the cement mortar consists of sand, cement and water. Those are the components. Components are the substances present in a mixture. So components of cement mortar are sand, cement and water. You all know sand and cement are powdered substances, solid substances, whereas water is a liquid. So here we are mixing components of different physical states. If we take the next example, cake. This contains sugar, flour, water, coloring and butter. Here again, you know that sugar, flour and butter are in the solid form, whereas water and coloring are in the liquid form. So here again, we mix components, more than one components are mixed together. We usually beat the cake mixture so that it gets mixed very well and then we make the cake. So there also we use components of different states. The next one, well water. So the main component is water. In that there is dissolved oxygen, so that is a gas, dissolved carbon dioxide, again a gas, and various salts. So those are solid. So here you can see well water is a mixture of solid, liquid and gases. Water, the salts are the solids, water is the liquid and the different forms of gases. But finally, the mixture is in the liquid form. You cannot see the gas particles there, or you cannot identify the salt particles in water. They all mix together and form a uniform mixture. Then the seawater. Again, it has water, dissolved oxygen and salts such as sodium chloride, magnesium chloride, magnesium sulfate and calcium sulfate. I am sure you know the chemical formulae of all these substances. Sodium chloride is NaCl, magnesium chloride, MgCl2, then we have magnesium sulfate, MgSO4 and finally calcium sulfate CaSO4. So those are the ions present here. So these are solid components. Water is a liquid component and the dissolved oxygen is a gaseous component. So again a mixture made up of components which are in different states: solid, liquid and gas. But as I said before, you cannot differentiate and identify what the salts are or the oxygen is. It all looks the same. So it is a uniform mixture. So that is sea water. These are some examples that are there in nature. With these, we will move on to more detail. It is very important to mix the components of a mixture well. When we looked at the examples, I mentioned that the well water and sea water are uniform mixtures. You cannot see the difference in components. They are all mixed together and they exist as one component. And if you taste the sea water, it will have to have a certain composition. So there the components of that mixture is mixed very well. Those are natural examples. There are many instances in our day-to-day life where it is very, very important to mix the components of a mixture well. The first example, making colors by mixing paints. I am sure students, many of you all can paint very well. There might be very good artists among you all. So there you mix colors. By mixing two colors, you get different shades. For example, you mix red and yellow, you get orange. But by mixing more red, you can get a dark orange. Less red and more yellow, you get a lighter orange. So like that, you can mix blue and yellow, get green. You can get different shades of green. And when you get that shade, it has to be uniform throughout the painting that you are going to do, depending on what you are going to paint. You might want to change the color. The gradient can be changed. You can start with a dark shade and go on to light shade, or you can have the same shade. But in your painting, the composition is very important. The composition of paints, that is the mixing of colors in a paint. The same way, when you paint the walls of a building, the color has to be uniform unless you want it to be shaded. So either way, if you want a uniform color, the paint mixture has to be the same throughout. If you want the color to change uniformly, or if you want to have a shading, then you have to change the mixing in a particular way. So either way, the mixing of paints is very important so that you can have a uniform color or shade. Have a uniform color or shade. That gives the quality to the paint or the wall. So this depends on what your requirement is. Then the components used to make cake. Again I mentioned this. We beat the cake so that all the components mix well. Say we put egg, we put flour, we put sugar, we put butter. If there is too much of sugar in one part of the mixture and not enough sugar in another part of the mixture, then the cake will not have a proper taste. If there's too much of egg in one part and there's not enough egg in another part, then one part might become too soft, another part of the cake will become too hard. So there is no proper mixing. If you want a proper cake, a very nice tasty cake, you need to mix the components well. So again, to get a good quality product. So here again, to get a good quality cake. So in these two examples, we see the word quality. So mixture has components. If the components are not mixed properly or not mixed well, then the quality of the mixture will be lost. So in order to have a good quality mixture, the components have to be mixed well. Then we have the next example. The medicinal property of tablets, capsules or liquid mixtures. Here not only the quality, the quantity is very, very important. All of you all are familiar with medicines. So if you have a headache or a pain in your leg, you need to take a tablet. Then there is a certain amount of medicine that has to be present in that tablet. You all know when you take a bottle of a tablet or a foil, they give certain instructions. In that, sometimes they specify the dosage based on the age of the person or the weight of the person. So you have to look at all those carefully and take the medicine. If you don't take enough, that is, if you take less than the prescribed amount, you won't be relieved of your pain or headache. The same way, in order to get a quick relief, if you take too much of medicine, then that can be harmful to you. So therefore, you have to stick to the dosage. So when we say dosage, that depends on the composition of the mixture. If they say this tablet contains this much, the whole tablet has to contain that amount of the medicine. If you break it into 2 pieces, each half should contain the same amount of the medicinal component. One can't have more and the other can't have less. They have to be equal in every aspect. So for that to be obtained, the mixing of the components in the medicines are very, very important. So these are some examples where we need to know we need to have good quality mixtures, as well as we need to maintain and understand the quantity of components in the mixture. So here we talked about dosage and the quantity of the medicinal component. Okay. So as I said, the quality of the mixture is important. The component should get mixed well as the amount of components present in the mixture is also important. To understand this, we will do an activity. Activity: study how the components are distributed in a mixture. Take about 500 milliliters of water into a beaker. Add about 10 grams of clay soil to it. Stir well and allow to stand still for about 1 minute. So this is the first picture. You can see a mixture containing clay soil dissolved in water. Then after we stand it, you can observe how it will look like. Then filter the muddy colored water into another beaker using a piece of cloth. Allow to stand still for about an hour and see whether the muddy color is uniformly distributed throughout the solution. See if the clearness of the solution is similar from top to bottom. So here we are going to observe the uniformity in distribution of the particles, those are the components of the mixture, whether it's uniform throughout the solution, and also we have to observe the clearness of the solution. I am sure you are very familiar with these observations. Take a piece of a metal sheet with a lustrous surface. You know what luster is, the shiny surface of shiny nature of metals. Take 2 identical drops of the solution from 2 places A and B. Here you can see A is the top of the solution and B is at the bottom of the solution. With a pipette or a glass rod, place them on the spots marked as A and B respectively on the piece of metal and let them to vaporize. So this is the metal plate having both samples A and B. Then we allow the water to evaporate, and after that happens, you will or you might get a residue remaining at points A and B. So what we have to do is we have to observe and see whether the residual matters at point A and point B are the same or different. From that, we can get a better understanding about mixtures. So here, as I said, this is initially when we mix the water, allow it to stand, then we filter the solution, that is the second one. We get the filtered solution, again allow it to stand for about an hour, and after that take 2 drops from different positions. We place it here and vaporize the water. And here again you can observe the amount of residual matter that is present in these 2 spots. So this is a very simple activity, students. I am sure you already have seen these observations. You know what it has to be. Let us observe what happens there. Can you observe this? At the top of the mixture, you can see it more clearly. Although it's brown in color, the color is very much light at the top, and when you go down towards the bottom, you can see the color increases. And towards the bottom, Now at the bottom, you can see there are more solid components. But since this is a filtered solution, you can see the change in color gradually. So students, to confirm that the components are not distributed evenly, what we can do is we can take a drop of the mixture from the top as well as the bottom onto this metal foil, or you can use a metal plate. Here I will take a drop from the top and place it on this metal plate, as well as I will take a drop from the bottom of the mixture and place a small amount there. So I have the 2 samples of mixture from the top surface on my left hand side and from the lower part of the mixture on the right hand side. So if we take this metal plate and heat it, maybe using a candle, so then we can see how the particles are distributed in this mixture. So let me do that now. So now students, I have the plate after heating it. Now you can see here, this side we don't see any mark. There are no soil particles here. Whereas in this side, the drop I took from the bottom of the mixture, you can see there is a small amount of soil particle remaining there. So from this observation, there are particles of soil here, there is nothing on this side. So from this observation, what can we conclude? If we take a unit volume of the mixture from the top surface and we heat it, then there is no soil particles. But from the bottom, when we take a unit volume of the mixture and observe the amount of soil particles present, we do have a small amount. So that means the distribution of particles throughout the mixture is not uniform. It's less at the top and more at the bottom. That means this mixture is classified as a heterogeneous mixture. A mixture where the components are not distributed evenly, or the composition is not uniform throughout the solution, is known as a heterogeneous mixture. So a mixture of soil dissolved in water is a heterogeneous mixture. Okay students, you saw the observations. You saw as the soil was dissolved in water, how it looks like. It looks like a muddy water. It looks as if the mud is spread throughout the solution almost equally. But when you let it to stand, you will see that if there are stones or if there are any other heavy particles, they all deposit at the bottom. The particles or the components that don't really dissolve in water. Then we filter the solution. We take the part that is on top. We remove the residue. And then we have the second solution. So in that, after letting it to stand for an hour, you will see the composition, the solution is not uniform. You would have observed clearly that near point A, this part, the solution is more clear, and this part, the solution is more muddy. That is because the components are distributed unequally, or we can say the components are not distributed uniformly throughout the mixture. That is why you have a more muddy, darker color solution at the bottom and a more clear solution towards the top. And after drawing drops using a pipette or a glass rod, we placed it on the metal plate and we evaporated the solution. After evaporating or allowing the water to vaporize, you saw the residue. There was less residue here. It was hardly noticeable. And there was more residue there. So that means near the bottom where we have point B, there is more soil dissolved in water. That is why we get a higher amount of residue. But in the upper part where the solution is very, very clear, there is very small amount of clayey soil dissolved. So again, from this we can conclude that the components are not distributed uniformly throughout the solution. And also the color is also different. So therefore, the physical properties, color, the texture, amount of substance were not uniformly distributed throughout the solution. So the conclusions from the activity is that we can say the components were not distributed uniformly in the mixture. That is the first one. Then we can say physical properties. Like color is not uniform throughout the mixture. So from this observation, you have got some information and understanding about a certain type of mixture. The above activity leads to the following conclusions. So as I told you all, there are a few conclusions that can be drawn from the activity. In the mixture formed by dissolving clay in water, the color or transparency is different from place to place. You saw that from the top, that is point A, the transparency was more. That is, there was less color, the solution was more clear. Whereas in point B, towards the bottom of the solution, it was more darker in color and it was less transparent. The solution was not clear, it was very muddy. So that is what we mean by color and transparency is different from place to place. Why is this? The reason is the amount of clay particles in a unit volume is different from place to place. So if we take the solution as a whole, it has a certain volume and there is a certain mass of soil dissolved in it. And if you take a unit volume of the solution, let's say if this is a unit volume. As we saw before, since this is point B, here the amount is more. More soil. That is why less transparency, darker color. Whereas if you take a unit volume from this part, unit volume from point A, here there is less soil particles. Here there are more soil particles. So that means the distribution of particles is not uniform. The amount of clay particles in a unit volume is different from place to place. So therefore, we can say that the composition is not uniform. Composition is not uniform. So that means, are there solutions that have uniform composition? I'm sure you know the answer, yes. We will do another activity to observe a solution or a mixture that has uniform composition. Activity: study how the components are distributed in a mixture. Again, a similar one. Take about 250 milliliters of water into a beaker and add about 10 grams of pure salt into it. Earlier we used soil, here we use salt. So here salt dissolved in water. Stir till the salt dissolves and filter the solution with a piece of cloth. Same as the previous activity. Allow to stand still for about 1 hour and see whether the clearness of the solution is equal from top to bottom. So initially we have the salt solution. After standing for 1 hour, later you can see the resulting solution. This is something that you already know. If you take a drop, if you had made it with pure water and a good amount of good pure sample of salt, then you can taste it. Otherwise, you should not taste it. So, if it is the cooking salt and water that you drink at home, you can taste the solution. I am sure you know the salty taste at the top and the salty taste at the bottom will be the same. So, here we have the solution. After 1 hour, you will see the observation. Then we take drops, again 2 drops. From this point, I can name it as A, and this point we will name it as B, like in the previous activity. We take drops of the solution from the 2 points, but you have already observed that the solution is a clear, transparent solution. So, then you transfer the 2 drops or few drops from each point A and B onto a metal plate, and the metal plate has to be a shiny metal plate, a lustrous one, and then you heat it so that the water evaporates off. And once that happens, you will get the residue remaining at the 2 points A and B. And here we have the cloth. Here they have said to filter it using a piece of cloth. That is why the piece of cloth is shown to you. This is to vaporize water. So once you do this activity, you can see whether this solution is similar to the previous solution, that is the clay mixture, or whether this is completely different from the clay mixture. So let us look at these observations. So here you can see, students, a clear transparent solution is obtained when sodium chloride is dissolved in water. So if the transparency, composition and color are all uniform throughout the mixture, you can observe that here we call it the homogeneous solution or homogeneous mixture. In other words, we can just call it as a solution. Okay, students. So you saw the observations clearly. You saw that the solution was very clear and it was a transparent solution. So once we dissolve salt, and after 1 hour, you still get a clear, transparent solution. And we mark this point as point A, somewhere here as point B. And from there, we transfer the drops and allow the water to evaporate. Then what will you get? Equal amount of residue at A and B. So that is what you can observe in this activity. From this, what can we conclude? The salt solution, the transparency or the color is uniform throughout the solution. Therefore, the particles in a unit volume of the solution is equal. So, the contents or the components are distributed uniformly throughout the solution or throughout the mixture. So, here the conclusion is the transparency or color is uniform throughout the mixture. And the components present in a unit volume is the same. Components present in unit volume of the solution is equal throughout the mixture. So this is what we can conclude from the activity. Let us look at the conclusions again. Following conclusions can be drawn from the above activity. In the mixture formed by dissolving salt in water, the transparency is equal throughout the solution. The amount of salt particles in a unit volume of the solution is equal throughout the solution. So that means we can say that the composition is uniform throughout the mixture. So from the two activities, y'all can clearly understand the two main types of mixtures. A mixture where the composition is not uniform throughout the mixture, and a mixture where the composition is uniform throughout the mixture. So that means we classify mixtures into two main types based on the uniformity of distribution of particles in the mixture. So let us look at these two types according to the nature of distribution of components. So what I told you all before, nature of distribution of components, mixtures can be divided into two categories. The first category, that is the salt solution, is known as homogeneous mixture. Here, the composition is uniform throughout the mixture. And the example we saw is the salt solution. It was a clear, transparent solution throughout the mixture. And the second type, you have already guessed, is the heterogeneous mixture. Here, the composition is not uniform throughout the mixture. And the example we saw is the clay dissolved in water. So students, now you know the two types of mixtures. And here the word homo means same type. So the composition is uniform throughout the mixture. Hetero means different. The composition is different throughout the mixture. So if you can remember the name, you know what the solution is or the mixture is. With that understanding, we will learn in more detail the two different types of mixtures. Homogeneous mixtures. The mixtures in which the components cannot be observed separately from one another, and the properties and composition are similar throughout are termed homogeneous mixtures. So here you cannot be observed separately, and the properties and composition are similar throughout the mixture. Then we call it a homogeneous mixture. In a homogeneous mixture, the physical properties, we observe that the salt solution is transparent, clear. So those are the physical properties. Physical properties such as color, transparency, and density are identical everywhere. If we can check the density of the mixture throughout, the density will be the same throughout the solution. So all the properties are similar. Homogeneous mixtures are also known as solution. We call it salt solution. That is because salt solution is a homogeneous mixture. So there are many examples for homogeneous mixtures. What we saw now is salt solution. So that is one example. If we take the glucose solution, you all know you might have done this before. When you need a lot of energy, you tend to consume a little glucose. Either you just eat the glucose or you can dissolve it in water and drink it as a solution. And if you dissolve glucose in water, you get a homogeneous solution. Sugar solution. Solution. Even many of the solutions that are available in the lab. If we take copper sulfate solution, different acids, HCl, hydrochloric acid, or other acid solutions. These are all homogeneous mixtures. Even we saw the copper sulfate solution in the first activity. You saw it was a uniform, clear blue color solution. So the transparency, color and the density will be equal throughout the mixture. So therefore these are all solutions. So then the next type, that is the heterogeneous mixture. Heterogeneous mixtures. The mixtures in which the components can be distinguished from one another and the properties and composition are different throughout are known as heterogeneous mixtures. So here components can be distinguished from one another and the properties and composition are different throughout the mixture. So hetero, I said, is different. That's the meaning of the name. The physical properties of the mixture such as color, transparency and density are different from place to place in a heterogeneous solution. A good example of a heterogeneous mixture is a mixture of rice and sand. By mistake, if a little bit of sand gets mixed with rice, still you can see the rice grains and the sand particles separately. You can separate it by picking the rice grains, but that is a very tedious process and it will take a very long time. But still we can separate them by a physical separation method. So that is a mixture where you can identify the components separately. So therefore it's a heterogeneous mixture. So example here, rice and sand mixture. Similarly in the lab, if you have small pieces of iron and small pieces of copper, and if they are mixed together, still you can see them separately. The color will be different. Iron is silvery metal and copper is a reddish color shiny metal. So you will be able to identify the two metals in the mixture. That is another example. Mixture of pieces of iron and copper. Then if we take lime water, that is calcium hydroxide dissolved in water, or calcium carbonate dissolved in water. A small amount will dissolve, but most of it will deposit at the bottom. So there you will see the distribution of the components is not uniform throughout the mixture. So therefore it is a heterogeneous mixture. So here calcium hydroxide dissolved in water. This is called lime water. So that is also a heterogeneous mixture. Now we will move on to the next part where we look at this activity. Dissolve the following substances in water and record the observations. So here they want you to do this by yourself. I'm sure you can get most of these things at home. So you can take equal size glasses, the water glass, so that it's transparent. You can observe the solution clearly, and to each glass maybe you can label them. Now if there are about 5 or 6, let's say there are 5 substances. So you take 5 glasses. Let me see. Common salt, washing powder, laundry blue, that is added to clothes, copper sulfate, potassium permanganate, wheat flour and ethyl alcohol. So you will need 7 similar glasses, water glasses. If we are doing it in the lab, we can use 7 similar beakers. We can label each of the beaker, take equal amount of water, equal volume of water. And also here we don't have to measure each substance, but we can take equal amount, say a teaspoon, half a teaspoon, or a yogurt spoonful of each of these substances. The solid substances, put it into each glass containing water, try to dissolve it completely, let it stand for some time and then observe. Okay students, so today we are going to observe how different solids and a liquid dissolve in water. So to do this activity, I have different substances here. The sodium chloride, that is the normal salt that we use at home. Copper sulfate solid, you can see here. Then potassium permanganate solid, washing powder, and here is wheat flour and also ethyl alcohol. Out of all these substances, you can see the first 5 are solids. And you can observe the solids differently. This is a white color crystalline powder. Copper sulfate is a blue color crystalline powder. Whereas potassium permanganate, that is condis, it's a black color or very dark purple color which looks like black, and that is also crystalline. Then we have the washing powder and flour. These are substances that are used at home. Then we have the colorless liquid, that is ethyl alcohol. Now I have already dissolved all these substances in equal amounts of water. Here you have to observe how the solution is. Look at the transparency and the color of the solution. So let me show you. Here you can see this is sodium chloride. The solid sodium chloride dissolved in water gives a clear solution. So the transparency is there. It's a transparent clear solution. Then we have the copper sulfate solution. Here you can see that is also a blue color transparent clear solution. Again we have the third solution here, that is potassium permanganate dissolved in water. That is a purple color clear solution, and that is also transparent. Then we have the next one, that is washing powder. Here you can see students, At the top, you can see the form. Here, the solution is almost clear. But towards the bottom, you all can observe that there are particles remaining. That means the transparency and the color are not uniform in this washing powder mixture. We have the other solid, that is wheat flour dissolved in water. Here again you can see at the top it's very much almost clear, and towards the middle part of the mixture you can see there is a pale color, and at the bottom you can clearly observe that there is a solid substance present. So that means here the distribution of the solid is not uniform, and the transparency of the solution is also not uniform. Then we have the ethyl alcohol dissolved in water. That also you can see is a clear, uniform, transparent mixture. So if you look at all these solutions clearly or the mixtures clearly, you can see sodium chloride mixture, copper sulfate solution, potassium permanganate solution, and ethyl alcohol mixed with water. They all have uniform transparency and the color is also uniform. But if we take these two, that is the washing powder dissolved in water and wheat flour dissolved in water, the transparency and the amount of substance present throughout the mixture is not uniform. So this is how we classify these mixtures. These three which have uniform transparency, that means the solutes or the components are distributed uniformly throughout the mixture. Then we call them as homogeneous mixtures. Whereas the washing powder and flour mixtures, there the distribution of the components is not uniform throughout the mixture. So we call them as heterogeneous mixtures. So from this activity and from these observations, you will be able to identify clearly what homogeneous mixtures are and what heterogeneous mixtures are. So you will be able to classify these mixtures easily. So let's see. First one is common salt. That of course you all know for sure it is a homogeneous mixture. Common salt. Why? This is the salt solution that we prepared at the beginning of the lesson. So you saw the common salt solution. It is an example of homogeneous mixtures. Then we have washing powder. We use washing powder to wash clothes. You know that when we put a teaspoon or tablespoon depending on the requirement, if we put a small amount of washing powder into water, we mix it well with the hand, you put it into water and you dissolve it. Normally for washing purposes, we either dissolve it with our hand or if it's in the washing machine, it gets mixed automatically. Either way, you would have observed that all the washing powder does not dissolve in water completely. Most of it dissolves and forms the forminature, which is very useful for washing the clothes. But still, there are some solid particles or residue that remains in the mixture. So that means it's a heterogeneous mixture. So when you put the clothes into that washing powder mixture, washing powder and water mixture, you mix it well. If you don't wash the clothes completely, nicely, there can be some residue sticking to the clothes. So that means the washing powder mixture is a heterogeneous mixture. So I will write that here. Washing powder. Then we have laundry blue. Usually we get the laundry blue as a blue colored powder. We put a small amount of, very little amount of the laundry blue into a bucket of water, dissolve it well, and the white clothes are dipped into that laundry blue so that it gives that bright white color to the clothes, especially your uniforms. They get very dirty quickly. So to keep it white, we usually use the laundry blue. You might have experienced this if you don't mix the laundry blue properly, or if you mix it and allow it to stand for some time, leave it aside, you forget about it, and after some time you try to dip a white colored cloth into it and take it out, you can see there will be darker regions in part of that cloth and light blue color regions. That is because the composition of the laundry blue is not uniform. The same way, if you soak your white clothes in laundry blue and leave it for few hours, you can see at some parts of the cloth there will be darker color and some parts of the cloth will have light blue color. Again, that confirms that laundry blue is a heterogeneous mixture. So here laundry blue is a heterogeneous mixture. Then copper sulfate. I already gave you all that example. And we have observed the copper sulfate solution. It's a blue color, clear, transparent solution. So it is a homogeneous solution. Copper sulfate. Then we have potassium permanganate. Again, potassium permanganate is Condis. It's a dark purple color crystal. When you dissolve it in water, you get a purple color clear solution. So that means it is a homogeneous mixture. Potassium permanganate. Next we have wheat flour. Wheat flour is what you have at home, the normal flour. If you take a teaspoonful of flour, dissolve it in water, and if you allow it to stand for some time, I'm sure you know the observation. The flour deposits towards the bottom of the glass and you get a clear solution towards the top of the mixture. That means the distribution of the components is not uniform throughout the mixture. Therefore, it is a heterogeneous mixture. So, wheat flour is a heterogeneous mixture. Then we have ethyl alcohol. Ethyl alcohol is an organic solvent available in the lab and it is used in the household also for certain purposes, medicinal purposes. So, this is a clear solvent, a liquid. So, when you mix ethyl alcohol with water, you can see they mix well together and you get a clear solution. And the color and the transparency, because it's clear, it's transparent and the transparency is uniform throughout the solution. So, therefore, the ethyl alcohol mixture is a homogeneous mixture. Okay. So, now we have classified these mixtures as homogeneous and heterogeneous. I am sure you did it correctly and you know the observations, so you know why they are homogeneous or heterogeneous. Now let us look at some more examples. So here this is a table that contains some mixtures. In the mixtures, they have given you the first component and the second component. So that means there are at least 2 components present in the mixture. So mainly 2 components present in the mixture. And then they have given you the nature of the mixture, whether it's homogeneous or heterogeneous. And finally, how we name or term the mixture. How the mixture is termed. Let me take the first example. Wheat flour. We discussed wheat flour before. That is a solid, a white color solid, a powdery substance, white color powder-like substance. And the second component is water. Water, you know, is a transparent liquid, a clear liquid that's known to all of us. And when we mix wheat flour and water, you get a heterogeneous mixture. Here, wheat flour is a solid, water is a liquid. So when we term the mixtures, we start with solid, then liquid and gas. So here, since wheat flour is a solid, water is a liquid, we term it as solid, liquid, and since it's a heterogeneous mixture, solid, liquid, heterogeneous mixture. The next one is salt, sodium chloride. That is a solid. You all know it's a crystalline solid. And water, a liquid. When you dissolve and get the salt solution, it's a homogeneous mixture. And the components are solid and liquid, so we call it solid, liquid, homogeneous mixture. Then we have coconut oil and water. Now both of them are liquids. You have experience. Does coconut oil dissolve in water? No. Even if you take a small bottle, into that you take a small amount of coconut oil and water, close the lid, shake the bottle thoroughly. Initially you will see as if the two are mixing. You can see the oil droplets mixing with water. But once you stand it for about an hour, not even an hour, just 10 to 15 minutes, you can see that the water layer will be at the bottom and the coconut oil layer will be at the top. They separate into 2 layers completely. And at the interface, slightly the water and the coconut oil will mix with each other. So that means they don't mix completely well. Therefore, they form a heterogeneous mixture. Because both are liquids, we call it a liquid-liquid heterogeneous mixture. Then we have the next example, ethyl alcohol, water. What we discussed with the activity. Both are liquids, both are clear solutions, transparent solutions, and when you mix them together, the solution is transparent and the composition of the mixture is uniform throughout the mixture. So therefore, it is a homogeneous mixture and both these exist in the liquid state. Therefore, liquid-liquid homogeneous mixture. So from these examples, students, you can see we use the physical state of the components only. We don't consider the physical state of the resulting mixture. Solid liquid, although it's a liquid, we call it as solid liquid heterogeneous mixture. The first two are solid liquid. If both are liquids, obviously the resulting mixture is also a liquid. We will look at the next one. Sugar and salt mixed together. Both are solids. Both are crystalline in nature. And when they mix, it is a heterogeneous mixture. You can identify the sugar crystals separately from the salt crystals. You know what they are. So that means it's a heterogeneous mixture, and that is a solid-solid heterogeneous mixture. The next one, copper solid and zinc solid. You know these two are metals, copper and zinc. So if we take the symbol of copper, Cu, and zinc is Zn. When they are mixed together, it says here it's a homogeneous mixture. Now earlier when I explained, I said when you make small pieces of iron and copper, you can identify them separately. Yes, if you had copper and zinc as solid particles, if you just mix them together, you can differentiate them easily. But here what they mean is the alloy that is formed with these two metals. So here it is an alloy. That is why it becomes a homogeneous mixture. An alloy. So here what they do is they take 65% of copper and mix it with 35% of zinc. So to do this, if it's 100 grams, 65 grams have to be copper and 35 grams have to be zinc. They melt the two metals. Normally you all know metals have high melting points, but if you want to make shapes like jewelries or ornaments or vessels, normally they melt it and they mold it into a shape. So here both the copper and zinc are melted. We take the molten copper and molten zinc, that is the liquid form, and mix it together. Once it gets mixed completely, it becomes a homogeneous mixture. Then you allow it to solidify, and that results in the alloy that is called brass. So here brass is an alloy. Alloy means mixture of more than one metals. So this has to be homogeneous. Just imagine you have a copper vessel at home. If the bottom part of the copper vessel has more copper, it will have a certain color and it will have a certain texture. And if there is less amount of copper at the top of the vessel, that means that will have a different texture and color. Then that particular vessel will not have the expected quality. The brass will not be of good quality. Instead, if you had brass that is uniform in composition, and if you make a vessel out of that brass, then of course it will have very high quality. So if we want to make an alloy, the brass, using copper and zinc, then the two have to be mixed thoroughly and the mixture has to be homogeneous. The next one, carbon dioxide gas, hot water. So it's a gas and water is a liquid. Here you have heterogeneous mixture. Gas, liquid, heterogeneous mixture. Whereas carbon dioxide gas, cold water, again liquid, is a homogeneous mixture. Now what is this? Both are the same gas, carbon dioxide gas, and the second component is water. But you can see here, this is hot water, this is cold water. And hot water, it's a heterogeneous mixture. Cold water, it's a homogeneous mixture. This is something that you would have seen at home. You take water into a vessel and you boil it. You do that in your day-to-day activities. What do you see? How do you identify it starting to boil? From the gas bubbles going upwards. So once the water starts becoming hot, you see the gas bubbles starting from the bottom moving upwards. That's the initial point of heating. Why does this happen? Normally, carbon dioxide can mix very well with cold water. There, you cannot differentiate the dissolved carbon dioxide separately from water. We have discussed this in your grade 10 biology lesson when we discussed the properties of water, good solvent property. Because oxygen gas dissolves well, the aquatic organisms can breathe easily. Similarly, carbon dioxide also can dissolve in water. But that dissolves well when it is cold water. But the amount of gas that can dissolve in water when it is hot is less. Therefore, when you heat water, when you try to boil water, with the increase in temperature, less and less amount of gases dissolve. Therefore, the gas is evolved from water. So, if you want to get water without any gases, oxygen or carbon dioxide, you have to heat the water or you have to boil the water. And because at high temperature with hot water, you can observe the gas bubbles clearly and you can differentiate the carbon dioxide gas from water. We call it a heterogeneous mixture. But when the temperature is less, if it is cold water, then you cannot differentiate the water from carbon dioxide gas, or you cannot identify the carbon dioxide gas present or dissolved in water. Therefore, it is a homogeneous mixture. So, here the name or the term is gas-liquid heterogeneous mixture if it is hot water, and gas-liquid homogeneous mixture if it is cold water. So, from this table, I am sure you have a good understanding about how different states of components, solids, liquids and gases can mix together and how they form different types, that is heterogeneous or homogeneous mixtures, and how we can term these mixtures. An assignment. Prepare a list of mixtures used in various occasions in the laboratory and day-to-day life. State the components in the mixtures. Differentiate them as homogeneous and heterogeneous. Indicate how those mixtures can be named according to the state in which the components exist. So, this is similar to the table that we discussed in the previous slide. You have to write examples, identify the components and say whether that is homogeneous or heterogeneous, and then you term the mixture. I will show you a few examples, then you can gather information or you can observe the different types of mixtures available in your household as well as the laboratory, and you can classify them. So, first, if we take the sodium hydroxide solution. You know sodium hydroxide is available in the lab. It is there as white colored pebbles. So, that is a solid. When you dissolve it in water, you get a clear uniform solution. So, that will be a homogeneous solution. So, if I write the mixture, sodium hydroxide solution. Hydroxide solution, and the components are NaOH, that is in the form of a solid. I'll use the first letter to denote the physical state, solid, and water. It is a liquid, therefore this will be a solid liquid homogeneous mixture. So if we write the name solid liquid homogeneous mixture. Another example from the lab. I have told you all about this before, calcium hydroxide. If we take calcium hydroxide solution, that is CaOH twice, again in the form of a solid, and we have water in the form of a liquid, and if you dissolve calcium hydroxide, you will get a heterogeneous mixture. So this is going to be a solid liquid heterogeneous mixture. These are two examples from the lab. Similarly, you see a lot of mixtures in your day-to-day life. Let me give some examples. Okay. Let's take G1. You know what G1 is. We have this example in our textbook also. A substance containing enough salts that is necessary to hydrate our body. So we take a sachet of G1E and according to the specification, we dissolve it in water. So that is a salt mixture. Salt means not the sodium chloride salt, it contains lots of salt. So G1E is a solid and we mix it in water or we dissolve it in water. It is a liquid. So what type of a mixture is this? A solid liquid mixture, and after dissolving G1E in water, it is a clear, transparent, uniform solution. So that is going to be a homogeneous solution. So this is going to be a solid liquid homogeneous mixture. We'll do one more example. Let's consider coffee. You take coffee and put it into hot water, or you dissolve coffee in hot water. I'm not talking about the instant coffee, the normal coffee powder which you get from the coffee seeds. So when you stand that solution for some time, what happens? The solid coffee component deposits at the bottom. So you get a residue and a more clear solution or more clear coffee towards the top of the mixture. So that means it's a heterogeneous mixture. So if we consider coffee, coffee is a solid mixed with water, so liquid, therefore again it's going to be a solid liquid heterogeneous mixture. So here you can see two examples from the lab, 2 examples from the household. And in all these, the components are solid, liquid. But you can get any example where you have 2 solids or liquid and gas or solid and gas. You can get enough examples for different types of mixtures. It can be homogeneous or heterogeneous, and the components can be of any physical state. So, I am sure now that you have understood this section of the lesson, you can prepare a list of mixtures used in various occasions in the lab and day-to-day life. And you can identify all these mixtures. So, with that, I will move on to a new topic, the solubility of substances. Solute and solvent of a solution. So, I told you all we will discuss about solubility. In order to understand solubility, first you need to know what solutions are and what solvent and solute are. We discussed before that homogeneous mixtures are also known as solutions. What are homogeneous mixtures? A mixture where the composition and the physical properties are uniform throughout the solution. So, then that is a solution. A homogeneous mixture is also called a solution. And in a mixture, you already know there can be 2 or more substances. So, here those substances or the components of a mixture are classified into 2 types. One is the solvent, the other one is the solute. So, a solution is composed of a solvent and 1 or more solutes. So, there will be 1 solvent and 1 or more solutes that make up the solution. Remember students, 1 solvent, 1 or more solutes. And if we understand solvent and solute more clearly, you will know that the substance or the component that is present in high amount in a mixture is known as the solvent, and the component or components that are present in lesser amount in a mixture are known as solutes. So, that is why you can have only 1 solvent and more than 1 solute. So, here if we define or if we explain solvent, the component that is present in large amount, and the solute, the component or components present in lesser amount. So, if we look at some examples, we have been discussing about mixtures. We'll consider the most common one, salt solution. In that, sodium chloride is the salt and water is the liquid component. Sodium chloride is the solid component, water is the liquid component. And you know this gives rise to sodium chloride solution. In this, normally we take a beaker of water and put few teaspoons or tablespoons full of salt. Even when we cook at home, normally we use table salt for food. There, to a large amount of water, we add only a small amount of salt. So, according to the explanation, what is the solute? Sodium chloride. And what is the solvent? Water. So, sodium chloride solution contains one solvent and one solute. But if you take the seawater, as we discussed before, seawater has many salts dissolved in it. Sodium chloride, magnesium chloride, sodium sulfate, magnesium sulfate. Like that, there are many salts dissolved in it. But if you consider the volume, the water is in very excess amount. But the salts are comparatively present in smaller quantity. So that means in seawater, water is the solvent and all the salts are the solutes. Likewise, if we take copper sulfate is the solute and water is the solvent. So here we can write this as CuSO4 solution, that is copper sulfate solution. You can write it in words or you can give it using the chemical formula, copper sulfate. And when you learn in higher grades the way of writing the physical state, we usually state it as AQ, aqueous, because it dissolves in water. CuSO4 aqueous means copper sulfate solution. But for us, if we can write only copper sulfate solution, that is more than enough. Likewise, a solution of sugar. We dissolve only a small amount of sugar in a larger volume of water. So, in a sugar solution, sugar is the solute, water is the solvent, and we get the sugar solution. So, in all these three examples, you can see, students, water is the solvent. We have discussed this in grade 10. Water is a good solvent that is very useful for living organisms. That is seen here. It can dissolve a lot of substances, a very good solvent. And all these are different types of solutes. So here you understand what a solution is and the two main components, solvent and solute. But there are more than one type of solutes that we have seen here. In addition to water, there are other solvents. What we use at home, kerosene, thinner to dissolve paint, grease, substances like that. Even oil, coconut oil can be a solvent. So, there are more than one type of solvents. And there is a way how different solutes dissolve in different solvents. That is what we call as solubility. So, to understand solubility further, we will discuss two activities. Solubility of a solute. So, here you have to understand the term solubility. To understand this, we do the first activity. Measure 100 milliliters of water into a clean beaker. Weigh 100 grams of pure salt, sodium chloride. Add salt little at a time into the beaker of water and stir with the glass rod to dissolve it. So, what do? We take 100 milliliters of water and this is sodium chloride, that is also 100 grams. This is the solvent, that is the solute. What we are going to do is, we are going to add sodium chloride into water. Here, if we do the activity in a quantitative manner, where we weigh all the substances accurately, then you have to initially weigh 100 grams accurately. After that, add salt little by little into water. Mix it well by stirring with a glass rod. You add a very small amount, mix it, and you have to wait until you see that everything is dissolved. Then you add a little bit more. Like that, you have to keep on adding salt and dissolving it until you come to a point where no more sodium chloride will dissolve in water. So, we add the sodium chloride into water and dissolve it. Finally, there will be a point reached where you have the sodium chloride solution here, but there will be a small amount of sodium chloride solid remaining in the solution. After this point, even if you keep on stirring the solution, the sodium chloride or the salt will not dissolve. If you add more salt, that also will remain as a solid. Then we call this solution as a saturated solution. That means it has dissolved, the solvent water has dissolved the maximum possible amount of salt that can dissolve in it. And at that point, we call the solution as saturated solution. So, what we have done is, by adding sodium chloride to water, we have prepared a saturated solution. That means we have dissolved the maximum possible amount of sodium chloride in 100 milliliters or 100 centimeter cubes of water. If you read the rest of the procedure, do not add more salt until the salt added before dissolves completely. When no more salt dissolves, this part, stop adding more salt and weigh the remaining amount of salt. Approximately, what is the maximum mass of salt that can be dissolved in 100 milliliters of water? So, here, after reaching this point, still there will be some salt remaining. We need to find that amount. So, the remaining sodium chloride, we need to find how much this is. So, then you can calculate the amount of sodium chloride that has dissolved in the solution or that is present in the solution. That is one activity. So, here, as you are familiar with dissolving salt in water, I am not going to do it as a quantitative one. I will try to dissolve sodium chloride and compare with the next solution. The solution that we are going to prepare in the second activity. So, I will move on to the next slide. The second activity, weigh 10 grams of calcium hydroxide at the laboratory. So, calcium hydroxide is CaOH twice. Take 100 milliliters of water to a beaker and dissolve calcium hydroxide in it. So, again here we take a beaker, we take 100 milliliters of water And in a watch glass, here we are going to take calcium hydroxide, but we will take only 10 grams of calcium hydroxide. So this is only 10 grams. Earlier we took 100 grams of sodium chloride. Here we take 10 grams of calcium hydroxide. You must be wondering why. Maybe you have already understood what will happen here. Let us see. Then what do we do? Take 100 milliliters of water to a beaker and dissolve calcium hydroxide in it by adding a very small amount at a time while stirring. So same as before. You add a little bit, mix it very well, stir it very well, so the calcium hydroxide will dissolve with water. Stop the addition of solid when no more calcium hydroxide dissolves in the solution and weigh the remaining solid. Approximately, what is the maximum mass of calcium hydroxide that can be dissolved in 100 milliliters of water? So here also, once we dissolve, we will get a saturated solution of calcium hydroxide. So this is going to be calcium hydroxide solution. And in that also, there is going to be calcium hydroxide solid remaining. So that means it is a saturated solution, and we will have a small amount of calcium hydroxide remaining in the watch glass. So only a part of the calcium hydroxide dissolves in water. So this is an activity that we will do in the lab. Let me do the activity now. Both activities will be done together so that it will be easy for you all to compare the results or the observations. Okay, students. So now we are going to see how the solubility of different solutes vary. To observe that, we have to do two activities where we use the same solvent, that is water, and the same volume of the solvent, 100 centimeter cubes or 100 milliliters of water. To that, we add two different solutes. One is sodium chloride, common salt, and the other one is calcium hydroxide. So here you can see both are solid components, and this is 100 grams of sodium chloride. Here I have 10 grams of calcium hydroxide. So first I'll take equal volumes of water using the measuring cylinder. I can measure 100 centimeter cubes of water. Okay, so I have the 100 centimeter cubes of water in both beakers. So to the first beaker, I will add sodium chloride. So I'll take 1 teaspoonful of sodium chloride. We will dissolve it well. You all are familiar with this observation. You know that sodium chloride can dissolve well in water. So to this again, I'll add another spoonful of salt. One more. I will leave this solution to stand for some time, and with that time, if there is any more solute, that will also dissolve. If not, before comparing the results, we can dissolve it again. At the same time, I have the second solute, that is calcium hydroxide, Again, I will use 1 spoonful of calcium hydroxide and dissolve that. Here also you can observe as if the calcium hydroxide is dissolving completely. But you can see a difference in the two solutions. The sodium chloride solution is clear. It's a transparent solution, whereas here you can see the calcium hydroxide is not transparent. It's a milky color solution. So, since I added 3 spoonsful of sodium chloride to this, I will add another 2 teaspoonsful of calcium hydroxide into this other mixture, so that we can easily compare the nature of the two mixtures. There is a little bit more of the sodium chloride that is not dissolved. So, I am dissolving that as well. So, now students, I dissolved 3 teaspoons of salt into this solution and 3 teaspoons of calcium hydroxide into the second beaker. The solvent is the same, water, volumes are the same, 100 milliliters of water, but the solutes are different, sodium chloride and calcium hydroxide. We can also do this activity by weighing the solutes and comparing the total amount of solute that can dissolve in water. But here I am going to compare how the same amount of solute dissolves in the same solvent. So, here you can see in both we got clear solutions first. The sodium chloride is transparent and clear, but here when I mixed calcium hydroxide into water, it became a milky solution. Now that I have kept it for some time, you can see still the sodium chloride solution is clear and transparent, and all the sodium chloride solid has dissolved in water. But if you look at this calcium hydroxide, you can see that the solution is changing. At the top, the solution is becoming more clear, and at the bottom, although initially it looked as if calcium hydroxide dissolved in water, now you can see the solid depositing at the bottom. So, from this, what can we infer? More sodium chloride will dissolve in water. Very less amount of calcium hydroxide dissolves in water. Now, here we took 100 grams of sodium chloride and only 10 grams of calcium hydroxide. Even if I put some more sodium chloride and dissolve it, you know that it will dissolve in water. So, obviously, more amount of sodium chloride dissolves in water compared to the calcium hydroxide. So, from this, we can confirm that the solubility depends on the nature of the solute. That is one. Further, if we take these two solutions and heat them, I am sure you know what will happen. There will be more solute that dissolves in water. So, when we increase the temperature also, we can increase the solubility of these two substances. Okay, students. So, you saw the activity in the lab. What happens when you try to dissolve sodium chloride in water and calcium hydroxide in water. We took the same amount of water. We took 100 milliliters of water, and here also we took 100 milliliters of water. To one, we took 100 grams of sodium chloride. To the other one, we only took 10 grams of calcium hydroxide. And what did you observe? That more sodium chloride dissolves in water. As I told you all before, I weighed the initial substance 100 grams of sodium chloride and 10 grams of calcium hydroxide. But when I dissolved, you saw that more amount, about 3 teaspoons, or the spoon I used, 3 spoons of sodium chloride dissolved completely in water, whereas only few, about 3 teaspoons of calcium hydroxide dissolved in water. So, we took 100 grams of sodium chloride but only 10 grams of calcium hydroxide. Even from that, there was a lot of calcium hydroxide remaining, whereas a lot of the sodium chloride dissolved in water. So, from this observation, what can we conclude? That sodium chloride dissolves more in water compared to calcium hydroxide. That is the conclusion we can take. So, if I write the conclusion here, more sodium chloride dissolves in the same volume of water than calcium hydroxide. So, that is one conclusion. The solvent is the same, the solutes are different, the volume of the solvent is the same, and we did the activity simultaneously during the same time. So, the temperature is also the same. So, only difference is the solute, and sodium chloride dissolves more, calcium hydroxide dissolves less. What will happen if we heat these two solutions? I told you all before, when you dissolve a maximum amount of solute, you reach a point where the solution is saturated with the solute. You cannot dissolve any more solute. But if you heat it, you have this experience at home. You would have made tea or coffee or hot milk. At least you would have dissolved sugar in hot water. Room temperature water maybe when you make lime juice. And if you had made cool drinks, still you would have dissolved sugar. In which water does sugar dissolve more? Obviously in hot water. You can dissolve sugar in hot water very quickly, whereas it takes a little time to dissolve sugar in room temperature water. But if it was cool water, the water you get from the fridge or refrigerator, the cool water takes a longer time to dissolve the same amount of sugar. So, you know the relationship. The same way, what will happen if you try to dissolve salt and calcium hydroxide in 100 milliliters of hot water of about 80 degrees Celsius instead of water at room temperature? So, here hot water, room temperature. This activity was done at room temperature. I will note it as T for temperature. If we heat the water, what will happen? Heat. So when we heat the solution, you will observe, students, the solute that remain in these two solutions. We try to dissolve the maximum possible, then a small amount of solid remains in the solution that will dissolve when we heat it to a higher temperature. And you will be able to see that you can add even a little more solute. You can add some more salt into hot water and dissolve it completely. The same way you can dissolve more calcium hydroxide. So when we heat the solutions, more amount of solute will dissolve in it. So that is the second conclusion that we can get from this activity. So at a higher temperature, we can say more solute will dissolve in water. So from these two, you have seen that the way different solutes dissolve in water is different. And also the amount of solute that dissolves in a solvent depends on the temperature of the solution. So those are two factors that can change the solubility. So based on these observations, we will try to define what solubility is. So in order to compare the dissolution of various solutes, another new term. Dissolution means the ability of a solute to dissolve in a solvent. In a given solvent, the amount of solutes dissolved in the same volume, here you have to note same volume of the same solvent at the same temperature. So here at the same temperature should be compared. I will read that again. In order to compare the dissolution of various solutes in a given solvent, the amount of solutes dissolved in the same volume of the same solvent at the same temperature should be compared. Therefore, solubility is defined as follows. So, when we define solubility, we say the maximum amount of solute that can dissolve in 100 grams of a solvent at a given temperature is known as solubility. I will write that down first. The maximum amount of solute that can dissolve in 100 grams of a solvent at a given temperature is known as solubility. So, in this definition, we fix the amount of solvent as 100 grams and we say at a given temperature. So same solvent, same temperature. In order to say the same volume, here we use the mass of the solvent. As you know, students, liquids can expand due to heat. So because of that, if we take a volume, that can change at different temperatures. But if we take the mass, that will not change based on temperature. That is why we use 100 grams of solvent. So for example, we take 100 grams of water, say at 25 degrees Celsius, and we dissolve different solutes. Then you will see that different solutes have different solubility values. So for example, if we take the solvent as water, so that is 100 grams of water, and the temperature as 25 degrees Celsius. We will consider two solutes. One is magnesium chloride. 53 grams of magnesium chloride will dissolve in 100 grams of water at the temperature of 25 degrees Celsius. If we take another solute, potassium sulfate, that is K2SO4, only 12 grams of potassium sulfate will dissolve in 100 grams of water at 25 degrees Celsius. So these are the solubility of these solutes. And from this, you can see the solubility of magnesium chloride is greater than the solubility of potassium sulfate. So that is what we have said here. In order to compare the dissolution of various solutes. So here we have compared the dissolution of two solids, magnesium chloride and potassium sulfate. If I compare and write the value, you can say solubility of magnesium chloride is greater than potassium sulfate in water at 25 degrees Celsius. So this is how we compare solubility of different solutes in the same solvent and also at different temperatures. So you have to understand different solutes have different solubility values, and the solubility of a solid component, a solute that is in the solid state, increases with increase in temperature. So that is why we specify the amount of solvent and the temperature when we define solubility. To understand solubility further, we will go on to the next slide. Factors affecting solubility. So to understand the factors affecting solubility, we will do a few activities. And the first one is effect of nature of solute on solubility. So we are going to test how the nature of solute affects solubility. We have already seen one example where we dissolve sodium chloride, that is salt, and calcium hydroxide in water. We use the same amount of water, but we use different amount of solutes. And there you saw that more sodium chloride dissolves in water compared to calcium hydroxide. Here, this is another activity where we use We'll look at the method. Take 50 milliliters of water at the same temperature into 2 small beakers. Accurately weigh 50 grams. Here the volume of water is different. 50 grams of each salt and sugar. Adding a little at a time, dissolve salt in one beaker and sugar in the other. When it comes to the point beyond which no more solid dissolves, stop adding the substance and weigh the remaining solid. See whether the amounts left are equal. So here again a similar activity, only difference is we use 50 milliliters of water and 50 grams of the two solutes. So here if I put it as a diagrammatic form, the two beakers both contain 50 milliliters of water. And to that we take the same amount of solutes. One is salt, the other one is sugar. Here we take 50 grams of the salt and sugar. And also temperature is the same. Is room temperature. So we maintain the volume of the solvent constant, we maintain the temperature constant, and we are going to do the activity at the same time. One after the other we will dissolve the solutes. So all the factors except the nature of solute is same. Why? We use two different solutes. Then, as said in the procedure, we add the salt and sugar separately into two beakers. We stir the solution well until they dissolve completely. We add them little by little separately and see the amount that can dissolve. So, we have to do this until a small amount of solid remains in the solution. And thereafter we have to weigh the remaining solute, that is salt and sugar. We can do that in a quantitative manner where we weigh the weight and compare the results. At the same time, you can just do it as a qualitative activity where you take the same amount, 50 grams of salt and 50 grams of sugar, 50 milliliters of water in two beakers, and you add the solutes, but at the end of the activity without weighing the substance that is left by looking at the substance. When you look at the substance, you can get an idea as to what is dissolved more and what has dissolved less. So from that also we can get a conclusion. So students, this is something that you can do at home as well. So what I want you to do is try this at home. You have salt, sugar, you can take equal amounts of water and you can dissolve the two solutes and see which one dissolves more. Okay students, now again we are going to observe the effect of nature of solute on solubility. So to do that, we have two different solutes. One is sugar, the other one is salt. And we will have to take equal volume of the solvent, that is 50 centimeter cubes of water. So first I will take 50 centimeter cubes of water to both the beakers. So I have 50 centimeter cube of water in one beaker. and to the other one as well. Okay. So now we have equal volumes of water at the same temperature. So solvent is the same, the temperature is the same. Only difference is the two solutes. So first I will dissolve sugar. So if I start dissolving sugar, we have to start with 1 teaspoon. We have to add it little by little and dissolve it. Similarly, I'll give it some time to dissolve. I will take the same amount of salt and dissolve it in water. So you can see when both the solutes dissolve, we get clear transparent solutions. Okay. Now I am going to add another spoonful of both the solutes, sugar and salt. So I am just doing this activity to observe how different solutes dissolve in the same solvent, to compare the solubility. So like this, we have to add more solute and dissolve them in water until it comes to a point where there is no more solute can dissolve in water. So students, when we keep on adding the two solutes, sugar and salt, you can see they dissolve in water. And here we have a completely clear solution of salt solution, and still there is a small amount of sodium chloride remaining in it. So when we do this activity, if we initially weigh the solute, that is the sugar and the salt, that I already did, it was 50 grams of both the solutes. Then we keep on adding them until the point where the two solutes don't dissolve anymore. After that, if you weigh the remaining solutes, then you will know which dissolves more. So this is an activity where you have to try this at home and find out what dissolves more. Okay. So if we come to the observation, you will be able to see that more sugar dissolves in water compared to salt. So at the same temperature, that is the room temperature, in the same solvent 50 milliliters of water, more sugar will dissolve compared to salt. So therefore, depending on the nature of the solute, the solubility will change. Solubility of salt is different from the solubility of sugar. That is one activity. Now I'll explain the next activity. Activity, effect of nature of solvent on solubility. So here we are going to test the nature of solvent. We already discussed the nature of solute. The materials required are a beaker, then we have sugar, that is the solute, and kerosene, that is the solvent. So again, we take a fixed volume of kerosene and also we will take water. So here we will use two solvents because we are going to test the nature of solvent on solubility. So the two solvents are kerosene and water. The same solute, sugar. What we will do is we will take 50 milliliters of water and kerosene into 2 beakers, and to each of the solvent we will add 5 grams of sugar. Same amount of solute to two different solvents at the same temperature. And using glass rods or spoons, you can dissolve the solute in the two solvents and see what happens to the solubility. Let me go through the method again. Take 50 milliliter each of the solvents, water and kerosene at the same temperature into two small beakers. Add 5 grams of sugar into each of them and stir. So this is also a very simple activity. You can do this and see how sugar dissolves in both water and kerosene. So we'll do this activity in the lab. Okay students, now we are going to do this activity to observe the effect of nature of solvent on solubility. So here the room temperature is the same and I have the same solute, sugar, and I have weighed 5 grams of sugar and taken it in filter papers. And here I have two different solvents of the same volume, 50 centimeter cube of water and 50 centimeter cube of kerosene. So the volumes are the same, only difference is the nature of solvent. So to the first solvent, I will add the 5 grams of sugar. Completely we have to add it and I have to dissolve it. At the same time, I will add the 5 grams of sugar into water as well. And I will try to dissolve that also. So here you can see it's only 5 grams of sugar. I will try to dissolve the sugar in water. You can see it dissolving and you can see it's a clear transparent solution. Same way I try to dissolve sugar in kerosene. Already you all can observe a small difference in the solubility. You can see sugar is dissolving fast in water, but almost all the sugar is remaining in kerosene. Nothing seems to dissolve in kerosene. So here almost all the sugar is dissolved in water. A little bit more sugar is there. Yes. So now the sugar has completely dissolved in water. Okay students, you can see here the 5 grams of sugar has dissolved completely in water, but almost the 5 grams of sugar still remains undissolved in kerosene. So from this observation, you can see the solid sugar crystal still remaining here. So students, you can see 5 grams of sugar has dissolved completely in water, but almost the 5 grams of sugar remains undissolved in kerosene. So here we had the same solute under the same temperature, but the solvents are different. Water can dissolve sugar well, whereas kerosene cannot dissolve sugar. So that means the solubility of a substance depends on the nature of the solvent. Okay students, So you saw the different observations. What did you see? 5 grams of sugar dissolves completely in 50 milliliters of water, whereas the 5 grams of sugar remains almost the same, hardly dissolves in kerosene. So when you compare the solubility of sugar in water and kerosene, it is high in water and very less in kerosene. So that means the nature of solvent affects solubility. So I will write down the observations and the conclusion. Observation: 5 grams of sugar dissolved completely in water. Only a very small amount of sugar dissolves in kerosene. So this is like almost doesn't dissolve. So here what is the conclusion? Solubility of sugar in water is high than in kerosene. Or in other words, we can say the solubility of a solute depends on the solvent. So I will write that as well. Solubility of a solute depends on the nature of the solvent. So that is the conclusion of the activity. So students, from these two observations, you have understood that the nature of solute affects the solubility, nature of solvent affects the solubility. So based on these two, the nature of solvent and solute, we can classify solvents and solutes into different types. Let me explain the classification. So to understand that classification, first we will answer this question. What are the factors that affect solubility? One factor is the nature of solvent. The other factor is the nature of solute. And there is a third factor which we have already discussed before. Why do we always say at a fixed temperature or at 25 degrees Celsius? Because the temperature also affects solubility. So the three factors are nature of solvent, then nature of solute and the temperature. So all these three factors affect solubility. When we talk about nature of solvent and solute, we need to understand the 4 different types of solvents and solutes. And temperature, as we have seen before, the solubility of solids increase with temperature. So, I will write that down here. Solubility of solids increase with increase in temperature. So, this is an example or a factor that you have already understood. At room temperature, less sugar, less salt or less calcium hydroxide dissolves in water. When you heat it, say to about 80 degrees Celsius, all of them dissolve in a higher amount. So, the solubility of solids increase with the increase in temperature. Now, we will see how we can classify solvents and solutes based on their nature. Solutes and solvents can be classified under 4 classes. So, we discussed that the solubility of substances depends on the nature of the solvent and nature of the solute. So, based on this and based on the bonds present in each of these compounds, we can classify them into 4 groups. You all know what organic and inorganic compounds are. What is an organic compound? A compound that has carbon as a constituent element. Inorganic compounds do not have carbon, but with the exception of oxides, that is carbon monoxide and carbon dioxide, carbonates like calcium carbonate and bicarbonates like sodium bicarbonate. These are all inorganic compounds containing carbon. So, that is familiar to you. Here we look at 2 new types of properties, the polar and non-polar property. That is also somewhat familiar to you. Water is a polar solvent, whereas lipids, fats are non-polar substances. So, when we combine these two, organic, inorganic and polar, non-polar, we get 4 types of compounds. So, the 4 classes, I can say polar, organic, polar, inorganic, then we have non-polar, organic and non-polar, inorganic. So, if we look at examples for these types. Now, we will take water. OH. This is the structure of water that you all know, and there is a negative sign there. What is this? A partial negative charge, and the hydrogens have a partial positive charge. So, when there are partial positive and negative charges, what does the molecule have? A polarity. So, here this OH bond is a polar covalent bond, and therefore, the compound becomes a polar compound. So, because of this polar covalent bond, water is polar. So, this is an example of a polar compound. And here there is no carbon, so therefore this is a inorganic compound. Inorganic polar compound. So again, if I write it, this is an example of inorganic polar compound. Then we will look at the next type. So if we have a compound like methane, you all know the structure. CH4 carbon with 4 hydrogens. When one of those hydrogens is substituted or replaced by a chlorine, then we have a compound like this. Chloromethane, or we call it monochloromethane. One chlorine in a molecule of methane. So this monochloromethane or chloromethane, this is a chloromethane. Now here, this is a polar bond. CCl bond is polar. So this is a polar covalent bond. Therefore, the molecule becomes a polar covalent molecule. And also, this is a molecule that has carbon. So it's an organic compound. Organic polar compound. So here, this is an organic polar compound. So now you know what an inorganic polar compound is, an organic polar compound is. Now in this, just because there is a polar covalent bond, the compound does not become polar. Now we will take another example. The same molecule, or let's say similar molecule, which has all 4 chlorines. Now CCl bond is polar. So here CCl bond is a polar covalent bond. But there are 4 polar covalent bonds, and if you look at the structure in detail, all these bonds, 2 bonds are opposite to each other. There are bonds like this, and there are bonds opposite and opposite to the first 2 bonds. So therefore, this polarity is cancelled off. We call these types of molecules as a symmetric molecule. It is a symmetric molecule. So when a bond that has polar bonds becomes a symmetric molecule, that becomes a non-polar compound. So this is a non-polar. So here you have to remember non-polar organic compound. So for this, there are many other examples like methane. Methane is of course non-polar organic. Carbon tetrachloride. This is carbon tetrachloride. Carbon tetrachloride. Even hexane. Hexane is another example. These are all examples of organic non-polar compounds. So we have looked at an inorganic polar compound, organic polar compound. Now we have a organic non-polar compound. But in these like carbon tetrachloride, hexane, even benzene, we will look at examples after this. There is no polar covalent bond. So a compound that doesn't have a polar covalent bond is a non-polar compound. If it has a polar covalent bond and if it is symmetric also, then it is not a polar compound. So again, if I write down the structure of CH4, there are no polar bonds. That is also a non-polar organic compound. Another example. Then the last type. If we look at the last type of compound, that is the inorganic non-polar compound. Molecules like carbon dioxide. This is carbon dioxide, CO2. Or carbon disulfide. These are inorganic and they are non-polar. So here these are examples of inorganic non-polar compounds. So students, I hope you understand what polar and non-polar compounds are. Remember, if there is no polar covalent bond, it is a non-polar compound. If there is a polar covalent bond and if the molecule is not symmetric, then it is a polar compound. If there are polar covalent bonds but the molecule is symmetric, then the compound is non-polar. So this is a lot for you all to understand. We are not going to too much of detail. I have just introduced what polar and non-polar compounds are. So compounds like ammonia, water, all these are polar compounds. After this, we will look at many examples of all these 4 types of compounds. So let me discuss some examples. Solutes and solvents are classified as organic, inorganic. So here organic carbon containing substances, inorganic absence of carbon, except oxides, carbonates and bicarbonates. Under that we have organic polar, organic non-polar, inorganic polar and inorganic non-polar. Now if you take alcohol, you all are familiar with alcohol. We have discussed about ethyl alcohol before. That is a polar solvent. So if you take alcohol and mix it with water, it mixes. So because it is a polar solvent. Before I go into detail about all these solvents or substances, there is something that you have to remember. When we talk about solubility or when we discuss solubility, we say like dissolves like. So here this is an important concept. Polar substances dissolve in polar substances. Non-polar solutes dissolve well in non-polar solvents. So you have to remember what are polar and what are non-polar. So when we say like dissolves like, polar dissolves in polar, non-polar dissolves in non-polar. So water is a very good example of a polar solvent. Oils are very good examples of non-polar solvents. So from all your day-to-day observations, you should be able to understand what are polar solvents and what are non-polar solvents. In addition to that, you are provided with many other solvents. You have to remember all these examples. Polar solutes are soluble in polar solvents. So here the same 4 groups of solvents and solutes are given to you. We will discuss some examples. I told you all like dissolves like. Polar solute dissolves in polar solvent. We can take any example from the given substances. Let me take alcohol, the first organic polar solvent. Alcohol is ethyl alcohol. When you write it as alcohol or ethyl alcohol, it refers to the same solvent. And the first inorganic polar solvent, water. They both dissolve well. Dissolve well or mix well. Why? Both are polar. Alcohol is organic, water is inorganic, but irrespective of that, because they are both polar, they mix very well. If we take acetone and ammonia, they will also mix well. So another example, acetone and ammonia. They also dissolve or mix well. Now here I have taken 2 substances, one from the organic side, the other from the inorganic side, but they are all polar. The same way, if I take alcohol and acetone, they are both polar and they are both organic. They also mix well. If we take water and hydrogen chloride is the gaseous state of hydrochloric acid, HCl. You know they dissolve very well. So here water and hydrogen chloride. That is HCl in the form of gas. So they are both polar substances, but they are inorganic. They mix well. So here this also mix well. So here you can see, students, these are all polar substances. So polar organic can mix with polar organic. Polar inorganic can mix with polar inorganic. The same way a polar organic can mix with polar inorganic substance. So here the important factor is that both the solvent and the solute have to be polar substances. You don't have to worry about the inorganic or organic nature of the substance when it comes to solubility. You have to remember whether they are organic or inorganic, but when you consider solubility, only the polar nature matters. So these are all examples for polar solutes which dissolve in polar solvents. Now we will look at some examples for non-polar solutes are soluble in non-polar solvents. So as I explained before, here we have non-polar organic substances and non-polar inorganic substances. So if I take an example, if I take organic substances, hexane and benzene. Hexane dissolves well or mixes well in benzene. Here the solvent and solute will depend on the amount that we take. If we take more hexane, that becomes the solvent, benzene becomes the solute. But if we take more benzene, because these are all liquids, if we take more benzene, that becomes the solvent and hexane becomes the solute. So that is why I am referring it to as mixes. So hexane and benzene, because they are both non-polar, they mix well. Same way, if we take carbon disulfide and liquid carbon dioxide. Carbon disulfide, you all know, is CS2, carbon disulfide, and liquid carbon dioxide, that is CO2 liquid. They are both non-polar, but they are inorganic substances. They also mix very well. The same way, if we take another non-polar substance, say carbon tetrachloride. Carbon tetrachloride can dissolve carbon disulfide or carbon dioxide. So, I will take the example as carbon tetrachloride and carbon dioxide, liquid carbon dioxide. All these mix very well. So students, these are examples from the solutes and solvents given to you. But you see many examples at home. Now say you have seen jackfruit. So when you take a jackfruit and cut, or if you haven't done it, you might have seen someone doing that. There is a latex coming off the fruit, a milky sticky substance. And if that sticks to the hand of the person who is cutting it, and if the person washes the hand in water, the latex cannot be removed. So what do? They take a little bit of coconut oil, try to dissolve and just rub it off so the latex is removed. Then they wash the hand with soap and water. So there, water you know is a polar solvent, whereas jack latex is a non-polar substance. So water cannot dissolve jack latex because one is polar, the other one is non-polar. But coconut oil is non-polar. So jack latex is non-polar, coconut oil is non-polar. It will dissolve in the non-polar solvent. The same way, previously in an activity we saw sugar and kerosene. Sugar dissolves in water. Why? Water is a polar substance. Sugar is a polar substance. So sugar dissolves well in water. But sugar is a polar substance. Kerosene is a non-polar solvent. So sugar does not or dissolves very less in non-polar solvent kerosene. So that is the concept. Polar dissolves in polar, non-polar dissolves in non-polar. That is what we say, like dissolves like. But polar does not dissolve in non-polar and non-polar does not dissolve in polar. That is what you have to remember. With this, we will discuss a few examples regarding solubility. This is also something I have explained to you all. Coconut oil, what will happen if you mix water and coconut oil? So this is coconut oil and here we have water. This is an activity or an example that is very much familiar to you. When we use lamps, sometimes oil lamps, what we do is we put a little bit of water. On top of that, we add oil and then light the lamp. How is that possible? Because coconut oil and water do not mix. So here they do not mix. They don't mix. They separate into layers. What is the reason? Coconut oil is non-polar. This is non-polar, whereas water is polar. So, non-polar and polar do not mix well. Even if you take a small amount of water and oil into a bottle, I have told you all this before, close the lid, shake the bottle well, you will see as if they mix together. But when you stand it for some time, you can see the two layers separating out like this. Water goes down and the coconut oil layer comes up. You all know the reason for that as well. Coconut oil is less denser than water, therefore that goes to the top, and water is more denser than coconut oil, so it settles at the bottom. So this is an example of substances that do not mix well together because of the nature of solvent and solute. So here, even if you heat the mixture, the solubility might increase a little bit, but they may not dissolve 100%. The substances that dissolve well will dissolve more when you heat them. So you have understood the nature of solvent, nature of solute, and the temperature affects solubility. And these are applicable to all the types of solutes. Nature of solvent and nature of solute is the same for all types of solutes. But temperature, as I told you all before, the increase in temperature increases the solubility of solids. Is it applicable to gases? Let me look at an activity. Solubility of a gas. So, solubility of gases depend on different factors. I told you all I will discuss an activity. Before I go into the activity, I will give you all an introduction to the solubility of gases. Generally, the solubility of a solid substance in a solvent can be increased by increasing the temperature. That is what we discussed a little while ago. But the solubility of a gas in a given solvent decreases with the rise in temperature. This is something that you have seen in your household. I am sure all of you have boiled water or at least seen someone boiling water. At room temperature, normally the water you drink is not pure water. It has lot of substances dissolved in it. Obviously, the good substances, the minerals are dissolved in it. There can be salts depending on from where you get the water, but it will be pure good water that you can drink. In addition to these substances, gases are dissolved in water. If you take water at room temperature, do you see the gases separately? This is water at room temperature. We don't see the gases separately. They dissolve well in water and you can't differentiate them. It looks like a homogeneous mixture. But if you heat or boil this water, let's say we boil the water, okay, that means it is at high temperature, is high. Then what do you see? You can see the gas bubbles escaping from water. So here you see the gas bubbles. I am sure now you can remember this observation. So why do these gas bubbles evolve? Have you ever thought about it? Now you know the reason. Because the solubility of gases decrease with increase in temperature. Here the temperature was less. The gas dissolved in water. You could not see the gas separately from water. So solubility is high at low temperature. But when we boil water, temperature increases, solubility decreases. Therefore, you can see the gas bubbles evolving. So this is something that you have to remember, students. Solubility of a gas in a given solvent decreases with the rise in temperature. So that is one factor you have to remember. Are there any more factors affecting the solubility of a gas in water? See what conclusion could be drawn from the observations of the following activity. Now we will move on to the activity. Activity. Observe how pressure affects the solubility of gases. So here this is another factor, the pressure of gases, or how pressure affects the solubility of gases. For this we need only two materials. One is a fizzy drink bottle. This has to be new and sealed. That means we have not opened the bottle for now. And also it has to be a plastic bottle. Okay, so it has to be new, it has to be sealed, and it has to be a plastic bottle. So that we know that there is gas dissolved. When I say fizzy drinks, the meaning of fizzy is that it has lot of gases dissolved in it. You might have seen the observation when you open the lid of a fizzy drink bottle, sometimes the gas flows out. The drink itself flows out because of the fizziness. So we make sure that it is new because it should have all the gas in it, and also it has to be a plastic bottle so that we can try squeezing the bottles. Then we need another bottle, the same type, same size, but an empty plastic bottle containing water. Similar plastic bottle with water. So that is the other material that we need. So what are we going to do here? We take the two bottles. One is the sealed bottle of fizzy drink, and this is a bottle containing the same volume of water. Here we make sure that we have the same volume of water and the drink, that is the fizzy drink. So here we maintain the volume constant, The temperature is the same and we use similar or almost like identical plastic bottles. So only difference is that this is a new bottle and this is an open bottle. As you know, students, normally the seal bottle has high pressure and an open bottle has less pressure. So this is what we are going to do. We take the two bottles, place it side by side, the new bottle of fizzy drink and the bottle containing water. We squeeze both the bottles simultaneously. You will see that the fizzy drink bottle does not get pressed, but the bottle containing water can be pressed easily. Thereafter, what I will do is, I will open the lid of the fizzy drink bottle. So, before I open, if you look at the two bottles carefully, you can see both the solutions are clear, transparent solutions. You won't see any other substance there. So, they are both homogeneous solutions. But when I open the fizzy drink bottle, you can see a change. The same way, when I open the water bottle, you might see a change, you may not see a change. Then after we open it, we leave it for some time. Again, if I squeeze the two bottles, try to press or compress the two bottles, you will see a difference. So that is the activity that we are going to do now. Let me go through the method again. We have two bottles. Those are shown in the diagram. Soda water in the closed bottle and water, and both are identical plastic bottles. Take an unopened bottle of soda water available in the market, and to an identical empty bottle add water in equal quantity to that of the soda water and close the cap tightly. So here water equal in quantity. That is what I said. The volumes are the same. And you have to close the cap tightly so that the rest of the conditions are the same. Now squeeze both bottles with hand and select the harder bottle. So as I explained before, in addition to this, I will open the soda water bottle and observe what happens, and thereafter again I will try to squeeze the two bottles. So this is a very simple activity. Let us do this in the lab. Okay students, now we are going to test or demonstrate how pressure affects the solubility of gases, or we will check and see whether pressure affects solubility of gases. Now I have two identical plastic bottles, so we can press it and try to squeeze it. Here this is a sealed bottle of aerated water and this is an open bottle filled with water to the same level. So everything is same except that this is an open bottle containing water and this is a new bottle of aerated water. So what I will do is I will try to press the two bottles from the bottom. If I press, you can see the bottle that contains water gets compressed a little bit. But I apply the same amount of force, but I am unable to press it and compress the bottle that contains aerated water. You all know the meaning of aerated water. There is carbon dioxide dissolved in this water. That is why we call it aerated water. So when there is carbon dioxide dissolved, we can't press it. So this is one observation. The reason for this is this carbon dioxide gas had been dissolved in this water or in this solution, aerated water, under high pressure. And since I have not opened the lid, still it is under high pressure. So I am unable to compress this bottle, but I can compress the second bottle. Here you can see, if I open this also, there is no evolving of gas. It's the same liquid water. Now I will open this bottle. You all are already familiar with homogeneous and heterogeneous mixtures. This is a homogeneous mixture at the moment because you can't differentiate between the water and the carbon dioxide dissolved in it. Now I will open this bottle a little bit. Now you can see the gas bubbles coming up. So now it becomes a heterogeneous mixture. Why? You can see the gas bubbles coming up. I will open it a little bit more. What happens here when I open the lid? The pressure is released, and because the pressure is released, the solubility of carbon dioxide decreases. Therefore, the dissolved carbon dioxide is being released from the solution. I will open it further. Here still you can observe the evolving of gas. Okay. So I will leave it like this until all the gas evolves. So here you can see when the pressure was released, the homogeneous mixture became a heterogeneous mixture. Now I will squeeze both the bottles. Now you can see, still I can squeeze this nicely, whereas I can squeeze this to a certain extent more than the previous instant. Earlier when it was completely sealed, I could not press it, but now I can press it. So that means the pressure has been released. So from this observation, students, you all observed two main things. A closed sealed bottle of aerated water is a homogeneous mixture, but once you open it, you can see the gas bubbles, that is carbon dioxide gas. So it is a heterogeneous mixture. And that gas, that is carbon dioxide, was completely dissolved in water due to the high pressure. So we can conclude that the increase in pressure increases the solubility of gases. Okay, students. So now you saw the observations of the activity to test the effect of pressure on solubility of gases. Initially when I squeezed the two bottles, the soda water and the water bottle, what did you see? It was very hard to squeeze the soda water bottle, whereas it was somewhat easy to squeeze the bottle containing water. So that was the first observation. Easy to squeeze the bottle with water, but difficult to squeeze the soda water bottle. Then when I opened the lid, what did you see? You saw the evolving of gas bubbles. Gas bubbles evolve when the soda water bottle is opened. And then again, we saw that it is easier to press the open soda water bottle. That was the third observation. It was easier to press the opened soda water bottle. So from these observations, what can we conclude? That gases dissolve more in water under high pressure, or the solubility of a gas increases with its pressure, or when the pressure is increased. That is what we can conclude from this activity. So, if I write down the conclusion. So, we can say the solubility of gases increase with increase in pressure. So students, we have discussed two factors. One is pressure, the other one is temperature. The solubility of gases decreases with temperature and solubility of gases increase with increase in pressure. That is the conclusion of this activity. With that, I will just write down the factors that affect solubility. So, the solubility of a gas in water depends on two factors. The first factor is temperature. Increases solubility, decreases, and pressure increases solubility, increases. So, there are only two factors. One is temperature, the other one is pressure. When temperature increases, solubility decreases. When pressure increases, solubility increases. So, students, with that, we have finished the discussion on solubility. You have to remember the nature of solvent, nature of solute, and temperature affects the solubility of solvents and solutes in the liquid and solid states. But the solubility of gases depends on temperature and pressure. It decreases with temperature, increases with increase in pressure. So, with that, solubility is clear to you. Now, we are going to move on to a new topic.